Okay, dynamic branch prediction. What do we mean dynamic? Dynamic has two underlying meanings. Number one, the outcome of the prediction can change for the same branch instruction. Okay, so the outcome is dynamic. Sometimes we say it's taken, it should have been taken. No, it should be a taken. Or sometimes we say it should be a not taken. That's one of the meaning. The other meaning is this is done during the runtime. Okay? And primarily here we mean it's done at the runtime. So why does prediction work? Because underlying algorithm has regularities. Data that's being operated on has regularities, and instruction sequence has redundancies that are artifacts of way that human compilers think about problems, okay? And then that's the nature about branch instructions. But what about dynamic branch prediction? Is it better than static prediction? Seems to be. In some cases, it may not be. But in general, it is true. There are a small number of important branches in programs which have dynamic behavior, like the branch control. So performance is a function of accuracy, cost of misprediction, plus what? Last time I told you there is another important factor. Plus what? Tell me what that is.
Can you repeat the question, please?
The question is this equation accurate? Is there anything missing in this equation? Okay. How much time and how big a circuit do you need in order to predict? Okay, so we can simply say that's the cost of the prediction. Okay, and we have learned what branch history table is. This table can never be of infinite capacity. So the table is usually 4K entries big. Okay, so there will be misses. How do you access the table? Using index, that's one way. Using full associativity, that's another way. Or using hash function, that's yet another effective way. Okay? So there will be misses. And whenever there are not sufficient locations, there will be tags needed. Okay, there will be tags needed. So we use lower bits to index into the table. If that's the scheme we use, then the higher bits will become the tag. And the information we kept in there, suppose it's a 1-bit value, indicating last time when we encountered this branch, did it branch? Then usually what we can do this time is to simply base our prediction on that bit. And usually we just follow suit saying this time it should branch or it should not branch, depending on what that bit says. Okay, so it says whether or not branch is taken last time and no address check, that's dangerous, but it's okay because it's prediction. If you want to be more precise, like if you're using larger table, trying to catch all the branch instructions, then you need tag. Or if you're using hashing, still remember hashing, then you need tags. Okay? And problem in a loop, 1-bit BHT will cause 2 mispredictions every time you encounter a loop. And if that loop really executes. So we improve the 1-bit scheme by using 2 bits for the prediction information. Okay, with 2 bits, then our predictor is less sensitive. even when it's wrong for once, it will not change direction right away. Okay? So we can absorb some sudden changes and remain confident on our previous path. Okay? But with 3 bits, in other words, we may have up to 8 states, then this predictor will be too irresponsive, too slow. Okay? Too fast is no good. Too slow is no good either. It's like the car shock absorber. Okay, you know the car shock absorber? We have a spring and we also have a damper, right? Why do we need to have that damper? If we don't have the damper, we simply have the spring. Tell me what will happen when you hit a bump. Okay, so we need to have a damper. However, if the damper is too sticky, what will happen again? Okay, so you know the damper will have to have some kind of, forgot
Grease?
what?
Grease?
Grease? What's that?
Lubricant?
Whatever. Okay, so BHT accuracy, when tested on these benchmarks, it will have this kind of misprediction rates. Okay, this is a simple statistic. So in order to make this table meaningful to you, you should test 2-bit predictor also and get lower miss rates. Everyone may be lower, some may be higher because that might be a particular unusual case. And then for 2-bit predictor, there are many possibilities. Like first, I told you we have 4 states. But maybe you decide to use only 3. It's up to you. Or even if you use them all, but maybe you have different edges, meaning that different kinds of transitions. I don't know. You decide how to transit these states. Okay? And even if you have the same transition diagram, you might decide to use these 3 states for taken prediction and only 1 for not taken prediction. It's all up to you. You should test all possibilities and choose the best design. Okay, so you use the final winner to compare it against these results, and then you should also try 3-bit predictors. Even more possibilities using 3 bits. And choose the final winner and also do comparison and decide what you need to do. Okay, so maybe this is effectiveness of 1-bit predictor, 2-bit predictor, choose the best. 3-bit predictor, 4-bit predictor, 5-bit predictor. So the effectiveness may be this, and then this, and then this, and then this, and then this. Okay? When you catch the trend of the curve, then you can determine this is the best. If you don't try 3, 4, and 5, you never can tell 2-bit is the best. Okay? How to design and experiment to find out the truth is very important. Second-class scientists can design experiments to collect a bunch of data, yet don't know how to explain them. Agree? You are going to work on your research topic. You are going to design experiments, and most of those experiments will be nonsense. Okay. So this is simple. I'll skip all these. Okay, correlated branch prediction. I told you last time, if we have a main program and a subroutine, within the subroutine we have a branch if, when it's called by this instruction, or when it's called by this instruction, then this branch if may have different behaviors. So depending on where you are coming from, I might want to use predictor A or predictor B for my dynamic prediction. Okay? So depending on where you're coming from, oh, that's too complicated. Because for a subroutine, the color may be thousands. So you want me to have thousands of these? It's unlikely. So usually we simply look at the previous branch as being a taken or not taken. The previous branch to be a taken or not taken in order to decide which predictor I want to use. If you look at 2 branches back, the previous and the one before, then it could be not taken, not taken, taken, not taken, not taken, 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 4 cases. 4 cases, then maybe you use 4 predictors to choose from. Okay, so depending on how you got here, I used the correlated branch predictor for you. Correlation means the relationship. Okay, it's like the cases. Okay, so simple. If I look at 2 branches back, then I need 2 to the second predictors. And how many entries in every predictor? N entries. So this N is like 4096, and this M is like, look at 2 branches back, 3 branches back.
This is in addition to the address and tag matching.
Addition to, no, that's the table. This N represents how many entries you have in the predictor.
Because earlier you mentioned that we'd also store the address or possibly even do tag matching, right?
Okay, so what does this pair of number mean? It means how many and how big is each. Got it? Okay, how many? 2 to the mth. Because you're looking at 2 branches back, 3 branches back, whatever branches back. How big? 4K entries. And every entry will have a tag, will have branch prediction information, or sometimes even the target address in it. Question so far? Good. Let's go on. So you noticed one fact. That is, how you got here does matter. If it's from a taken, if I want to trace back 4 branch results, then I will end up with having 16 predictors. Would that be too big? 16 of these, would that be too big? Yes or no? In commercial use, we trace back 12 past branches. 12. So tell me how many branch prediction tables do we have? 4K. We have 4K such tables. How big is each table? Imagine, tell me how big a table would be. 4K such tables. And the table size is how many entries? You think?
Depends on how many bits we use.
Okay, every entry should contain target address, branch information, branch prediction information 2 bits. okay, valid bit, maybe tag. So 64 bits should be sufficient
64
for an entry. So how many entries do we have for each individual predictor? What do you think?
Too big?
What?
Still too big?
2B?
They have 12 and 12.
12 history branches.
So
Equivalent to, we will have 4K predictors. Okay? Every predictor means something like a 4K entry table. Every predictor is a big guy. So this time, you guess how many entries should we have in each predictor? 64 shouldn't be too many. Should be just a few, okay? And as a matter of fact, every predictor contains only one entry. So this is the real design used in Pentium. You know Pentium? Okay, so what they did was something like this. I used a shift register for the past branch history, 12 bits. Every time I have a new branch result, every time I see a new branch result, I record whether it's taken or not taken, 0 or 1, in here, and ship everything right by 1. Okay? With this, I have 4K possible history patterns. And every pattern, in other words, every path along which I got here, I use a branch prediction table. Okay. For every possible path pattern, I use a branch prediction table. So how many tables will I have? 0, 1, all the way up to 4095. I have 4K such tables. Since there are so many tables, so in every table, I have only one entry. Valid bit, prediction, information, target, and what else? Oh, tag. Every table has only one entry. So all these tables together is nothing but 4096 entries. Still an acceptable table size. Okay, it's just like how many K? It's already 32K bytes of storage. Already huge. Got it? It's important to look at something that are real. Okay? So 32K, is that acceptable to you now? Wow, already too big.
that's just for one branch, right?
Just for one, what?
That
For one branch?
yes.
No, it handles all the branches. It predicts all the branches. It works for the entire program. Okay, so that's something about global branch history. Global branch history. We used M-bit shift register. What is this M? The same M here. Okay, keeping the past and the latest M branches that have actually occurred, and predictors. All the predictors are n bit. Oh, I'm sorry. This n could mean number of bits we used. Okay, so number of entries, maybe it's not shown in this representation. Well, whatever, read the book. Okay, so this is a global branch history. If we keep only the record of past 2 branches, then we need 4 predictor tables. If we keep the past 12, then we need 4K of these. Then, as you can imagine, everyone cannot be too big. So this is a kind of correlating branch scheme. Okay, accuracy of different schemes. We have so many entries, only 1 predictor table, or unlimited entries, or so many entries, yet we trace back 2 branches. So in other words, we have 4 such tables, okay? In other words, these and these 2 have the same storage requirement. And this one has unlimited storage, okay? And they all use the 2-bit scheme. Okay? Okay, so the result is like this. And I don't like this table. I always would try to look for something called average. Okay, show me the average. Don't test on me. See how good I am reading these bar charts.
Wouldn't there also be an overhead with the unlimited entries?
What overhead do you mean? Here we only look at the result. We don't care how much time you spend to do prediction. Okay? Fast or slow, right, is counted as 1, as increment by 1, and incorrect is increment by 0, something like that.
But we should take time into account because it has to finish.
Always, always. If you don't care about time, then I'll speak slower to save energy. Nowadays, everything should be low power. Okay, let's go on. This is a kind of design. May not be the best, but it shows you how it works. Okay? Okay, now forget about this. Let's look at these tournament predictors. You know predictors may have different designs. For instance, in my CPU, I have 1 predictor, the other predictor, and every time I encounter a branch, I ask both to predict. And when the result comes out, then maybe one is right, but the other is wrong. Or maybe last time this is the winner. So this time, although both are right, I still think this is a better one. Okay? Whenever I have a preference, next time when I encounter a branch again, I let them both do prediction. But I'll take this to proceed with my instruction fetch. Okay? So, do you get the idea? We let these 2 to compete with each other. And whichever wins, next time I'll trust it. So that's the so-called tournament, competition. Okay? You may use more C, D, depending on how rich you are.
This is basically replicating the entire prediction scheme. Basically, all that we just discussed previously is replicating and having multiple predictors.
And they're not exact duplications. They may differ in some way. They are different predictors. Otherwise, if both will have the same result. What's the meaning of letting them compete with each other? Okay. Okay? So far so good? Okay, let's skip all the details. So here we have global predictor, local predictor. What do I mean? I mean, like, I have erased some of it. Remember, I kept the record of past 12 branches? That's so-called global information or global predictor. And each of these tables are called local predictor, local prediction table. Next, comparing predictors. Well, skip this. Just use different schemes and let them compete with each other. Of course, every time someone wins and someone loses. Okay, so you want to be the winner or you want to be a loser? Easier to be a winner or easier to be a loser? What do you think? The answer is trivial. Do winners have better lives or do losers have better lives? Okay, so that's the pending form is prediction rate per 1,000 instructions, not per branch. So another way to look at branch prediction effectiveness is, since every program may have different frequency of branch occurrences, right? The weighting of branches in a program differ from program to program. So another way of looking at branch behavior is, for every 1,000 instructions, how many misses, branch prediction misses will there be? Okay? Just use different matrix. Whichever matrix you prefer, use it. Okay, right or wrong. Okay, so we talked about prediction. That just tells you the direction, whether you should jump or you should not. Another thing is, if you want to jump to where, that's another story. So last time I told you, the instruction set architecture design determines if the target of a branch instruction will vary or will never change. Remember? So in RISC, usually we say branch if and then immediate, which is the PC offset. And once your executable gets loaded into the memory, your PC value will never change. Okay? So your PC plus immediate will also never change. In other words, what happened before will be useful forever. All you need to do is to simply record it and then look it up later when you need it. Okay, so the target will never change. Okay, why will it not change? Because my instruction set architecture says so. However, if you design another kind of instruction set architecture, which says, no, this can be a register, then you need to develop another scheme to deal with this. Because every time this branch is encountered, you never know what the value of BR should be. So any previous record may not be useful. Okay, then your branch prediction will be totally different. So far, I don't know how to deal with this. Yet, there's another kind of branch instruction. What is that? Return. Tell me, how many branches do we have? One branch if, and then branch always, and then jump. Jump is regarded as a type of branch always, but with longer jump distance. Okay? And then call. Call is also a kind of branch, but that's again a type of branch always. Okay? But this call does not have to do with PC value. It has a fixed destination. Okay, that fixed destination does not have anything to do with the PC value. So if you call A here or if you call A there, you will always go to the same place. Yet another kind of branch is return. Return is trickier. Return always branches to wherever calls it. Okay, so return never should have a fixed target. How can you do? How can you deal with this? Somebody give me a smart idea.
Save the caller.
Save the caller. Smart. But what if it's a recursive call or nested call? Doesn't matter, because the callers will be revisited in reverse order. Okay? So save the caller address in a data structure which is first in, last out. What is that? Oh, a stack. Okay? So whenever you encounter a return, you save it. You save the caller plus one address in a stack. So this is return one. It's been called once. And then somebody calls return one again. Save it again. In what situation will return one be called? I should say this subroutine be called, and then before it really returns, be called again. Recursion, right? This is a kind of recursion. So can we deal with recursion now? Yes. Now things get more complicated. If someone calls return one, and then return one calls return three, return 2, and then return 2 calls return 3, and return 3 calls return 4. You see, different callers to different subroutines, everything got mixed together. So should we use 4 stacks or still 1 stack only? If we use 4 stacks, then of course these stacks can be activated by the return instruction address. Okay? But when I call, I don't know what the return address is. When I call to jump to the head of the subroutine, I don't know where the return would be. So I don't have an address for that stack. Or can I use one integrated stack for all the different calls to the same or different subroutines? Can I? Can I not?
You want to know which one was called when?
Which one is called when? I don't care. I just want to know the order. Do I need to know which one? Because the order is easy to know. Okay, we have only one time reference.
In a pipeline situation.
Oh, okay. All the calls will happen in the same stage. So they still remain in the correct order. One stack, multiple stacks. Go home and think about this. Next time when you have chance to learn the answer will be after the second exam when I explain the answers to you. Okay, are we done with this? Okay, that's branch target buffer. So branch target buffer deals with some kind of branches, but we need something else to deal with another kind of branches. The another kind means return. Okay, so whenever we want to store the target, then things becomes very serious. What do I mean? Which target does this, which branch does this target belong to? This becomes a very serious question. Okay? Don't attach this target to the wrong branch. Okay, so every target should be attached to the exactly correct branch. How can you do that with a shared data structure shared by all the branches, and the number of branches may be infinite? The only way to do is to keep a tag for that target. Okay, it's just like in the cache. In the cache, the space is never sufficient. If there are sufficient locations in a cache, then this cache will become useless. Okay, it's good simply because it's small enough. Okay, so we need to have a tag. Next, summary. Prediction becoming important part of execution. Why? Because in pipelining, control hazard is a very big issue. Branch history table, you already know what this is. And correlation, depending on the path along which I get to here, my branch behavior may be different. So I need to have different predictors for even the same branch. Okay? And tournament, some predictors may work better than the others. So when I have different designs, I want them to compete with each other. And I always choose the best to use. Target buffer. All these deal with the question of whether I should branch or not. But I still need to know where to go if I want to branch. So target buffer deals with where the target should be. And this cannot solve it all. We still have returns. So I'll give you a hint about the return target handling. That hint is return address stack. Go look this term up.
To calculate the predicted address, because the dynamic prediction happens in the first stage.
Okay, to calculate the predicted address, no, the addresses are never predicted. We're not that good to predict the address. The addresses are exact.
So you have to wait till the decode stage to actually get the...
No, we cannot do that. What we do is, the first time we encounter this branch, we wait until the result comes out. And then we store it. And from now on, whenever we need it, it's there. Okay, so first time, even if you predicted the direction right, doesn't help. Okay, it doesn't help because you never had the target before. or you want to predict the target, you have 1/4G chance to get it right. Okay, next, overcoming data hazard with dynamic scheduling. Advantages of dynamic scheduling. For static scheduling, I need to consider all the possibilities because I have a control flow graph. I don't know how the execution flow will go along this graph, along which path in this graph. But dynamically, things already happened. I know exactly where I am. Okay? And I know exactly what basic blocks I need to deal with. Let me give you some background information before I go on. You write a program, and in your program, this is the first branch if. So you may go here, and then this 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 may go here. Okay, how many possibilities do you know? Forgot. Maybe already 1K if I have 10 branches. Okay? So statically, I need to consider all the possibilities. Is it difficult? Yes or no? It's difficult because there are too many possibilities. It's easy because I have unlimited time to think, to arrange. But dynamically, I already know I was here, and then I come here, and then I did not branch this time, and then I go here. I already know this is my execution path. Only one single fact in front of me. Okay, is it easy? Sure, very easy. But is it difficult? It's also difficult because my instruction scheduling should complete in one cycle or no more than a few clock cycles. How long is a cycle? What's the cycle time? Nanosecond or even fraction of a nanosecond. You need to make decision. You need to check all the instructions you have at hand. So now do you understand dynamic nature of instruction scheduling? Let's see what really happens. What really happens is we have a computer here, CPU in particular. This CPU has a very efficient fetcher. This fetcher goes ahead very briefly to fetch as many instructions it can for you. Okay, so what does this fetcher do? This fetcher fetches, say, 4 instructions at a time. 1, 2, 3, 4. And whenever it fetches an instruction, it will check the branch prediction table to see if there is any branch. You see, it's with the PC value, we already can look the table up and discover if there is any branch instruction being fetched. Understand that? Do you understand that? Okay, no objection. I suppose you do. Okay, so you
How do you know it's a ground?
compare the PC value against the tags. Okay,
So in the first time you don't even know if it's a branch. You don't
how do you access cache memory? Also index and then tag comparison, right? So you do the same to the branch predictor table. If you can discover your memory access can be satisfied by the cache, then you can also discover if there's a branch in your fetch stream from the predictor table. Same reasoning, same operation. Okay, so if there is any branch, if suppose this one is a branch if, and suppose my table, my predictor tells me it's going to be a taken one, then I disregard this immediately and fetch from the target in the next cycle. Very quickly, I fill in new instructions. Should there be any branch? I don't care. My predictor will help me continue fetch new instructions. Okay, so very quickly, I will have many instructions at hand. How many? In the ancient Pentium case, 40 instructions. Nowadays, maybe up to 128 instructions in my table. Okay? Within this table, there are some predicted branches. Even with 40 instructions, I already may have 5 basic blocks. Right? Every basic block may be just 6 instructions. And here on average, everyone can be as large as 8 instructions. Okay? So to fill up the table with 40 entries, I already need to do like 4 branch predictions. Okay? So can you see now I'm fetching instructions along this path, okay? The red path, including multiple basic blocks. Can you see the fact now? Yes.
So the system can fetch instruction faster than the clock cycle?
Clock cycle? Maybe not. Maybe what you are saying is it can fetch faster than the back end can consume them. Okay?
So in one clock cycle, in this case, we fetch 40 instructions. Or that's just the whole table?
Okay, maybe in every clock cycle you want to fetch 4 instructions, 5 instructions. Doesn't matter depending on your fetch bandwidth. But anyway, you should always provide more instructions than your back end will need. Okay, otherwise this fetcher would become the bottleneck of the system design.
Is there a name for this table or just a fetch buffer?
That later I'll give you a name. Okay, so every time I fetch, every cycle I fetch 4 instructions. And among the 4, maybe only 2 are useful, right? The target may fall in the middle of the way. So this cycle I can fetch in only 2 useful instructions. And maybe for the next 4, the second is already a branch, so the last two will have to be discarded if I predict that branch to be a taken. Okay, so the fetcher bandwidth is at its peak maybe 4, but effectively maybe only 2.3 or something. Okay.
Could there be a stall because of that?
Maybe because you encounter a branch which does not have a target yet. So although for the first time you can arbitrarily predict it to be a taken or not taken, but without a target, a taken prediction will be meaningless. Okay? Okay, so all the instructions are placed in this we call buffer in order, and our dynamic scheduler will come in and check the instructions for their data dependencies and issue out whichever instruction is issuable at random order. Okay, so this table will lay in front of the CPU. And the back end, maybe the execution engine, will execute instructions at any random order. So once the instruction gets into here for execution, you never can recognize their ordering anymore unless you come back and check this table, look this table up. So here we do execution. Execution. The execution could be in order, could be out of order. For example, if this one doesn't go, then I will not let this go. Or if this one can go, then I'll check to see if this can go in the meantime. Okay, it can be in order or it can be out of order. If it's out of order, everything will be in a mass, right? A big mass. So some instructions will finish earlier than older instructions. Do you let it write the memory? Cannot. Do you let it write the register? Cannot. So if it generates some result, where can you place the result? The answer is, well, maybe if this one finishes early, okay, so we extend the table to also store any possibly generated result of that instruction. We extend the table to store the result too temporarily. Okay? So this table may also contain completed but not yet committable results. Okay? So eventually, let's regard the CPU placement as also along the timeline. Everything will happen from left to right. Then eventually, you need to complete the instructions and let the new instructions to be able to come into this table. Okay, give room to the new instructions. Okay, so how do you commit? The commit of the instructions will have to be in order. Okay, whenever you are ready to commit, you write to the memory or to the register, and then you can disappear from the table.
So we could have a lot of pipes waiting just in that commit state, on the last stage.
A lot of what waiting?
A lot of different stages in the pipe. Not stages, but...
Okay, so all these instructions may be at different stages in their life cycle. Okay, only those oldest and completed instructions can commit. And the commit bandwidth should be the same as the fetch bandwidth. Okay, if you can commit only one instruction at a time, then this whole design will not be much better than a single pipeline design. Okay, so there's a commit bandwidth. Peak bandwidth and effective bandwidth should be similar to the fetcher bandwidth. Okay? And then everything can be in a big char in the middle. Don't care what you do, where you do it. It's like fire at will. Bam, 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 bam. Okay, data flow type execution. Okay, does that mean speed? Yes. Okay.
But if there's an error, you have to undo a lot of...
Right, if anything goes wrong, then I'll check back in this table. Like this branch prediction was made wrong. What do I do? Easy, simply erase anything behind that. Okay, just reset the valid bits. Then they're gone. Okay, and then I refill the table and recreate the big mess. And if something goes wrong again, then I'll kill everything from that point up. Okay, so can you see how effective this table is? This table has a name. It keeps the order of the execution sequence. Reorder buffer is its name. Don't care about the details, but try to work on this, understand how it works, what kind of problems it can deal with. And there are many details which I have not covered. For instance, when a new instruction comes in, the new instruction always wants to fetch source 1 and source 2, right? How do they find their source 1 and source 2? From register file? Maybe no more, because the register file may not have the most updated value. From the reorder buffer? Maybe. But if your source 1 has multiple appearances in the reorder buffer as destinations, which one should you use? Of course, the closest one, the one closest to you. Okay? There's yet another complication. That destination may be available, may not be available. Then what do you do? Find the closest version that's already available. Doesn't sound right. Okay? So you always use the closest version, and then you may need to wait, you may not need to wait. Or you find nothing in the reorder buffer, then you need to go to the register file for that value. Okay, so there are some complications. Each and every one can make a very good quiz problem, don't you think so? You see, I'm giving you all kinds of hints. But too many hints is equal to no hint. Question?
Is there any possibility that the fetch bandwidth be exhausted?
What be exhausted?
Like the fetch bandwidth.
Fetch bandwidth?
Yeah.
What do you mean by exhausted? Not fetch fast enough?
Yeah.
Okay, everything will have a limit. So if the fetcher is not quick enough, then the execution components can still get instructions to execute from the buffer. Okay, do you remember I told you when the buffer would be useful? When the producer and the consumer are of the same speed or of the different speed. When can a buffer be useful? When the speeds are the same or different? Tell me. The buffer will be useful when the speeds of both the producer and the consumer are the same. If you think they should have the same speed, raise your hands. If you think they should have different speeds, raise your hand. Did you raise your hand? No. Right, the speeds will have to be the same. Otherwise, if the producer is faster, then the buffer will explode sooner or later. If the consumer has higher speed, then the buffer will be empty most of the time. So they should have the same speed, but the buffer will be useful when there is speed variation. when the speeds vary sometimes. Okay.
You mentioned that the commit has to be of the same bandwidth like of the fetch.
Should be.
Would
Okay.
that cause hazards?
What hazard?
If, let's say, there are 3-4 instructions committing at the same time to the same place,
Okay.
for example.
You should solve the hazard problem. Like 3 instructions all want to write to the same register, then you let the newest one, the youngest one to write. Okay, you use mux to choose. Okay, so there will be many kinds of hazards. We talk about controlled data and structural. These are general types of hazards. And they appear in different forms in different designs. Okay, in nature, there are only these 3 kinds. But format-wise, they have different looks in different designs. Any other questions? Okay, 10-minute break. So, dynamic scheduling. In dynamic scheduling, the hardware rearranges the instruction execution sequence to reduce stalls while maintaining data flow and exception behavior. We talked about data flow. The dependency relationships must be maintained. And we talked about exception behavior. In here, if anything goes wrong, then I just disable anything behind that. Okay, it handles cases when dependencies are known at compile time. In compile time, dependencies are sometimes very difficult to even remember. Things are too complicated, too many possibilities. And then it allows code that compiled for one pipeline to run efficiently on a different pipeline. So pipeline depth has to do with the dependency relationships, how many stalls you need. Okay? So for the same instruction set, for example, IA32, Intel architecture 32, in other words, x86 instruction set, we already have hundreds of different implementations, right? 86, 286, 386, and so on. Okay, everyone has a different design, especially from Pentium on. All the I should say from 486 and on. All the designs are pipelined. Okay, and pipeline design changes the dependency behavior. Furthermore, with dynamic scheduling capability, compiler doesn't have to work so hard to reschedule your instructions. Instructions can be in any arbitrary order. The hardware discovers dependency relationships. And hardware speculation, you see, when we have branch prediction, the execution can simply go on without having to worry about if the prediction is wrong. Okay? So hardware scheduling can eliminate single pipeline stalls. It can also eliminate multiple pipeline stalls. Okay, no matter how many pipelines you have, it can take care of it all. It can be in order, it can be out of order. Even if it's in order, I mean in order issuing, the completion can still be out of order. What does that mean? If I have a multiply and then an add, the add is going to complete in one cycle, but may not be the case for the multiplication. Multiplication can take 20 cycles. Okay, so the add will complete earlier. Can the add change any CPU state? No, not yet, because the multiplication may cause some exception, invalidating the result of the add. Okay, so even if they don't have data dependency, they still have control dependency. Control dependency means the ordering of the instructions. Okay, so we need to distinguish between fetch of an instruction, decode of an instruction, issue of an instruction, start of execution of an instruction, complete of an execution of an instruction, and commit of an instruction. Okay, so during the life cycle of an instruction, we need to identify different time stages. Okay, dynamic execution may cause the execution order of instructions to reverse. Okay, later instruction may get executed earlier, causing new data dependencies. I mean, causing new data hazards called write after read and write after write. In a single in-order pipeline, remember we have only read after write. And read after write is always important, something we must always abide by. Yet, for these two kinds of hazards, we never have to worry about them in a single in-order pipeline. But if it's single pipeline, out of order execution, even with one single pipeline, we begin to have these two kinds of hazards. How to deal with them? Reorder buffer is one way to deal with them. Okay. Another way to deal with them maybe keep everything in order, especially at the commit stage. Everything should commit in order. Okay, but if everything is commit in order, all the performance benefits are gone. No matter how fast you can go ahead, you will eventually have to wait. Okay. So here we focus on out of order dynamic scheduling. Because if it's in order, then there's no need for scheduling. Scheduling means rescheduling. Scheduling means creating a new order, right? If everything is in order, then no new order can be created. Okay, so here we focus only on out of order. In a simple in-order pipeline, we check both structural and data hazards in decode stage. And this decode stage can be nicknamed instruction issue stage. Okay, but if you want to do out of order issuing, then you need to have one extra stage. The extra stage will be issue and read operands. Okay, your operand read can be deferred, delayed for any arbitrary number of cycles. Let me show you why this is necessary. Previously, when you decode, you also do register read. But now, if this is your instruction execution sequence, let's call this the oldest instruction, the newest instruction. You are not decoding this instruction. And these instructions may still be pending, waiting for execution. Don't have a result available yet. Okay? So when you decode this instruction, I don't know how many stages we'll need. So I just put down arbitrary number of stages. Suppose first we fetch. This is still the same. Suppose we do instruction decode and register read. This is still the same. Okay, can we decode this instruction and recognize what it wants to do? Yes, we can. But can we read registers? Maybe not, because there are still pending instructions. Okay, so we cannot read right away. We may need to wait. What can we do? Split. Or in other words, take this out. Register read. We don't do it here. We wait for indefinite number of cycles until the results become available. Okay, wait until the results are out. Now you see why we need to split this stage into two. Okay, we still can do decode at will as long as we have the instruction. But the sources may not be available yet. Okay? That's why we need to split this stage into two. And this issue means I know what to do, but I'm still waiting for my raw materials to come in before I can start producing my result. Okay. Now, do you understand what dynamic scheduling means? Do you know what it needs to do now? The most well-known, world-famous dynamic scheduling scheme is called Tomasillo's algorithm. Mr. Robert Tomasillo, working for IBM in the 60s, invented this method more than half a century ago. So call it an ancient technique. But never call it an out-of-date technique, because this method is still the most effective one today. Okay, IBM, Intel, whatever designs still use it. Okay, is that a good introduction? Okay, let's see how it works. It's for that machine in 1966. That machine has very long memory latency half a century ago. Okay, no cache was invented yet. Everything will have to come from the main memory. And the main memory are still the core type memory. magnetic type memory. Okay? So reading a magnetic core or writing to it, especially when writing to it, is a very slow process. No, I said that wrong. Reading from it is very slow. How do you read a core memory? Sense the magnet field direction. In order to do that, you destroy the memory inside. So when you know the answer, you need to write it back again. Okay, so a read includes a read and a write. And for a write, you don't care what's in it right now. You simply write it. So write is faster. Okay, read is a destructive read followed by a restore write. Okay, so goal is to have high performance without special compilers. All the codes are already compiled. I don't want to change the executables. I simply want your hardware to take care of everything for me. Another thing is, in that machine, we have only 4 registers. Only 4 registers. Far from being enough. But after this instruction set architecture was designed for 5 years, 10 years, the electronic technology can already implement a lot more than 4 in your circuit. Okay, how can you take advantage of it? Without changing the code, you cannot change the code anymore. Especially the number of registers available. Let me tell you why. This is my instruction. My instruction has a fixed length, has a fixed field for the register specifier. If I reserved 2 bits, then it would be 2 bits forever. No way you can increase the number of bits without destroying the format. Okay? So the format tells 4 bits, period. No bargain. Yet hardware can help. Okay, why study a 1966 computer? Because this scheme is still the best in the world. All these processors still use the same scheme. Okay, these are very recent advanced designs. Okay, so let's look at this algorithm. It uses a distributed dynamic scheduling scheme. What do I mean by distributed? Look at the reorder buffer. The reorder buffer is some kind of like a centralized structure. Okay, it doesn't really do the control. But if we were to do the control too, then this scheme is called centralized. What do I mean by distributed? I'll show you later. Okay, and register renaming, a very important scheme to alleviate the right after whatever data hazard. Remember I told you, right after whatever data hazard is really not data hazard. It is really structural hazard. It's because you don't have enough number of registers. Okay? Let them have another location and then they will not conflict with each other. So it's really structural hazard. Okay? Remember, make sure you understand that right after whatever is structural hazard. Although we call it data hazard. Okay, let's skip all these details because later on this will become obvious to you. So right now I'm not going to go through them. Okay, this is the organization. And it is very important that you follow what I say here. I don't have a pen. Or is this the stencil? Is that the power switch or, or the stencil? Oh, it's a stencil. Okay. Okay. Let's see how it works. Let me use a different color. What color don't we have here? Let me use green. Okay. Instructions come in from here. Okay. So there will be instructions. Suppose this is an add. Then I immediately dispatch this add to here. This is the adder. Okay. The adder has some buffer locations for uncompleted or even unstarted add instructions. So whenever you fetch in an add instruction, you dispatch it right away to these buffer locations if there's available location. Okay? And then it needs source 1 and source 2. What do I do? Okay, we have only 4 registers. For each and every of these registers, traditionally, you know there is value in the register, right? But here we need 2 more things. First is this value valid? If it is, then I put a 0 here. Or if it is not, then I put a 1 here. Meaning, no, this value is out of date. The most recent value should be generated by, say, 3. What do I mean by 3? Check the whole diagram and you'll notice there are places where new value can be generated. Where are they? Remember load instruction, what does it do? Read in the new value. Okay, so load instructions will generate new values for what? Load a value into register. Okay, so load will generate new register values. Add instructions will generate new values for the registers. Multiply will generate new values for the registers. Will store generate new values for the registers? No, it only reads value out. Okay, so these red symbols mean locations where new value will be generated. Okay, maybe I shouldn't use 3. Maybe I use mode 1, meaning new value will be generated by the mode 1 instruction. Okay, so if this add instruction needs to read this register, it will first check the value base, knowing, no, this value is no more good. Your desired value will be generated later by mode 1. Got the idea? Okay, also this add instruction may generate a result for R2. What do you do now? Then you invalidate R2's value. And here you say, my new value should be provided by add3. Okay, see, I'm going to put this instruction in add3. So add3 will be the most recent producer of this register value. Got the idea? So any upcoming instruction will know R2 will be provided by F3. Got the idea?
This is in a single pipeline, right? Single level pipeline.
Here, this is the single and unique pathway which every instruction must go through in order. Okay, got the idea? So once the instructions are placed in these locations are what? These locations are the waiting zone, waiting for services. Okay, you reserve the right to be serviced. That's why they're called reservation stations. Okay?
Can two instructions reserve the same register?
Of course. Say, this one wants to write R2. This one also wants to read R2. This one also to write R2, and that one also wants to write R2.
So how does that handle
That
that?
R2 will only memorize the latest updater of it for the future reference. Okay? If anyone should need R2 of this guy, it already got the record. It remembers which reservations results it's waiting for. Okay?
But then how do the older ones finish commit?
I don't think you quite understand the whole thing. Let me give you an example. The example is my instruction sequence, this one writes R2, and this one reads R2, reads R2, writes R2, reads R2. Okay, let's see. When this one wants to write R2, it will identify itself in here. Okay, it will identify it in here. So these two will get the correct tag. We call that tag. It's like an indicator to whom the result will be produced. Okay? And then when this wants to write R2, whether this is done or not, anyway, I'll update R2's tag again. So this one will get the right tag again. Okay? Never can be wrong. Got the idea?
Let's assume the first write was not there or was not completed yet. Then
Okay.
that would be
Okay, so when this completes, it uses a common data bus. The common data bus, the name for this actually means it can broadcast its results to anywhere in the chip, in the design. So everyone will hear its broadcast saying, I am, say, multiply 1. The value I'm going to deliver is how much? Anyone needing that value will record it down in itself. Okay? And at this moment, R2 remembers multiply 1. So R2 will also record this broadcast value for later use. Okay? So this always keeps track of the latest value or the latest updater. And whomever needs what value is well linked to the producer. My source 1 says I need R2. So I come to here and find out R2 is not yet available. The latest version is still cooking by this reservation station that will produce a result. Remember, there are so many reservation stations, but the reservation stations can be divided into two kinds. One is those that will generate new register value. The other is those that will not generate new register value. Okay? Any that will generate new register value act as extra register storage locations. Okay, so you see R2 could be in here if it has a valid value, or could be in here, as well as could be in here, could be in here, could be in here, could be in here, could be in anywhere. So R2 can have up to 12 copies. 1, 2, 3, 4, 5, 11, 12. Okay? R2 could reside in 12 different locations simultaneously. See? This design is in fact provided 11 extra registers for you to use for out-of-order parallel execution.
So the renaming is...
That's register renaming. R2 could be renamed to anywhere here. R0, R1, R3 as well. Okay, depending on your needs.
The renaming is listed.
This is like the renaming table, but not all. Okay, it only says whether I have the valid most updated value or the most recent updater is whom. Yet there can be other R0 renamers inside, all related properly to its consumers. The same R0 consumers, on the other hand, are related to proper producers. There can be multiple producers, so the data dependency relationships are well kept. Got the idea? A very smart design, make sure you understand it. Yes?
How many reservation stations there are? Because I see that...
Here we have 14. 6 plus 3 plus 2 plus 3. But the number can be arbitrary.
But for example, we have like a specific set for add, a specific set for multiple.
Right. Right. If you think you should have more adds, then put one more here. If you don't have chip space, then see if which one is least utilized. Cross it out. Okay, that's the so-called optimization. Okay. Division, maybe this one can divide. Maybe this one can AND or exclusive OR. Okay, so these are some kind of ALUs, but with some special features. Okay, like adder design should certainly be somewhat different from the multiplier design. Okay, so you can combine them together, you can separate them, it's all up to you. Having these function units are just an example. This is like the checkpoint. Everything will be in order before the checkpoint. Everything after the checkpoint will be in arbitrary order as long as the data dependency relationship, true data dependency relationship is maintained. Okay? Any question? Other questions? Okay, then I'll go on. Let me ask you questions. Can we have two adders, one here and one there? This one has its reservation stations. That one also has its reservation stations. Can I do that? Can I do that? Make sure you understand the answer is yes. Or can I do this? I have two adders, two individual adders sharing 10 reservation stations. Can I do that? Similarly, I can. Why not? Because I don't care about what this is. I care only about which reservation I'm in. Okay? This is nothing but my tool. Like my screwdriver. Same screwdriver can be used by any mechanic. Okay? What matters is who I am in here. Another question. Should anything go wrong, this one has an exception. Can I precisely handle the exception and kill all the instructions, all the subsequent instructions? Can I? With this design? Yes or no?
Just clear everything and you go back to the...
Clear everything? Maybe these are still in execution. Oh, I'm sorry, I'm assuming this is the oldest and this is the newest. Okay, the other way around. Anyway, if anything goes wrong, can I still do precise exception? Can I? Can I? Do you still see when we fetch? Okay, after fetch, I don't know how long I need to wait until I enter into the decode stage. Okay, because that has to do with how deep my queue is. Okay? And then, after certain cycles of waiting, finally I get decoded. After decoding, I know where I should go. To this group, or this group, or this group, assuming there's available space. Okay, so decode, I go to here. Have I read the operands? Maybe not. So I wait for an indefinite number of cycles again until I get all the sources I need. Okay, see the waiting is in between? Okay, once I get all the operands I need, can I start execution? No, maybe not, because maybe two become executable at the same time. I need to arbitrate between the two. Okay, so maybe anyway, one will go first and the other will have to wait. Okay? Once I start execution, I know after how many cycles my value will be available. So when I finish execution, I simply broadcast my results and disappear. I don't care. Whoever needs my result will catch my result automatically. Nothing to do with me. I only do broadcast. Okay? But you haven't answered my question yet. What if an exception happens? Can I precisely accept?
You still have your reorder buffer?
No. Where is it? It's on the blackboard, not on the screen. So can we precisely accept? The answer is no. No way. So I don't know how to finish the whole thing up. But IBM 360 doesn't care Why? Because this is simply a floating point unit. Floating point unit, even until today, don't care about exception handling. It simply reports back to the integer unit. What do I mean by integer unit? The main controller. It simply reports to the main controller saying, something went wrong, I gave up. You restart the whole thing again, I don't care. Okay, no exception handling. No, I said that wrong. No precise exception handling. I just tell you, whole thing collapsed. Okay, got the idea? But if this design is used by the main controller like Pentium, we cannot let that happen. That's why later we will have to try to integrate my lovely reorder buffer here. How to integrate the whole thing in? Easy. Just keep the record and remember which where each of this instruction go. So when this instruction goes wrong, it will broadcast, right? And the reorder buffer needs also listen to the broadcast and be able to accept value into the proper location or precisely interrupt from the proper point. So the integration is not a very difficult task. I'll leave that to you. Very simple. When you dispatch, simply record where it goes in here and listen to the broadcast. So the common data bus, as you can already imagine, will be a very heavy interconnection to everywhere, and this also becomes the bottleneck. Very likely we cannot afford to have another set of common data bus. In other words, in every cycle we can only commit one instruction. With only one instruction committable, do you think that's a very quick design? Yes, why not? Because floating point instructions usually take tens of cycles, a few tens of cycles to complete. But for integer instructions, if every instruction takes only one cycle to complete, then one single common data bus may become the severe bottleneck. Okay, for different situations, the design will be different. So in 1966, one common data bus is far more than enough. But for integer type instructions, one single common data bus will become a very severe bottleneck. Okay? Okay, so what do we have in the reservation stations? We need to have, of course, OP code. So for the adder, I need to tell the adder whether I want to do unsigned add, signed add, subtract, whatever. I need to have source values, two sources. If the sources are not available, then I need to record where it will come from when it becomes available. Okay? And also I need to have a valid bit indicating this reservation station is in use. Just like a cache line, there must be a valid bit. Otherwise, there will always be zeros and ones inside. How do you know if that's trash or something useful? Okay, so the valid bit is very important, absolutely needed. Also, we need to know if this reservation station will generate a result, which register it wants to write to. Okay, 3 stages of Thomas-Roy algorithm. Now you understand why we have issue stage. Okay. After the issue stage, then we wait for the sources to become available indefinitely. Wait, let's see. When can we issue? Tell me, when can we issue? When there's an available reservation station. Okay. Or more precisely, when you get to the tail of the floating point queue and you found an available reservation station for you, then you can issue. After issuing, you wait indefinitely until your results are available. And then once you have the results, you start to arbitrate for the screwdriver that you need. Okay? So when you get the priority, you start execution. Right, if all the reservation stations are occupied, the only thing you can do is to block at the door, not letting anybody else to pass through. And you cannot proceed yourself. Okay, and then once you start execution, then how long it will take will become more deterministic. Okay, and when you are through, what do? After finish execution, what do? Broadcast? No, not yet. Get the right to broadcast. There's only one common data bus. You need to arbitrate for that resource again. So you wait indefinitely. So this is a very easy quiz problem. Show me where can be stalls and where cannot be stalls. TAs need to listen to my lecture very carefully. Otherwise, students will be smarter than you are. Okay, so maybe I said something wrong. When I'm in the reservation station, I need not to remember which register I need to write to. I don't need that information anymore. Because if the register still needs me, then it will record my ID. Right? So what I do is simply to broadcast. Therefore, the common data bus simply broadcasts, saying who I am and what the value is. It no more says where I want to go. And who I am is not important. Okay? This time, who I am is the only thing I need to tell the rest of the world. Okay, so it becomes a come from bus. It becomes a where is it? Okay, so the common data bus is like a come from bus, who I am. Okay, and previously our bus is like a go to bus, where I want to go. But who I am is not important. Okay, can you tell the difference? Okay, so that's a come from bus in nature. And the data structure of the bus is not important anymore. Okay. We use some parameters to exercise the design. We have a running example, many foils showing you how a code sequence is executed in the Thomas-Rousse algorithm. I'll stop here. And before I leave and leave it to the TA, I need to tell you something. Usually for an exam, the expected class average should be 60. More or less, okay? Yet today, our true, genuine average is way below that. I'm sorry. The quiz problems are not that difficult, but you didn't do very well. So what will happen then? Do you know? Come back and see me next semester? No, it won't be that bad. I'll level the average up to 80. Okay, so for the first exam, your average will be 80. For the second exam, your average will be 80 again. And in your presentation, maybe I don't do that again. But anyway, I'll calculate your final and make the average 85. In other words, if you are an average student in the classroom, then you are guaranteed to pass the course. Which is not a very good filtering mechanism. I should fail half of you to be reasonable. Okay, now do you get the idea? Now your genuine average is 36 point something, to your great disappointment. Is that good or bad? It could be good because it tells you how many things you do wrong, how many defects you need to correct, okay? Or it could be bad because it hurts your feeling. Good or bad, I leave it to the TA. So I'll come back next week. See you.